Well, thank you, Miller. So when Miller asked me whether I could give a talk here, I asked him if I could give one that is speculative, and he says no problem. So as you can see from the title, what I'm going to tell you about information processing in classical complex network is speculative, as in no concrete results have been obtained yet, but we believe it should be true. And then so any slide that you see a star would be speculative. And then I move on to speculate further on how information processing might be different in quantum complex networks. And those slides will come with 2 stars, 2 asterisks. Okay? So let me start by maybe educating some of you on what a complex network is, since I don't see any slides showing complex networks. I think you would be glad to find that there will be no equations in my slides, because the previous slides, there are lots of equations, but there are a lot of pretty pictures. So this is a complex network. There are 2 kinds of objects on a complex network. First, either you call that round thing a vertex or a node, and it depends whether you come from a mathematics background or you come from an engineering background. You prefer one over the other. And then the blue line that connects nodes, what you can call that an edge or a link. Again, this is the mathematician's terminology, and this is the engineering and physical sciences terminology. And this, a complex network like this, where you just have a bunch of nodes and you connect them together with lines, and you don't care really, you don't assign any special values to the lines themselves. It's called an unweighted network. But of course, we can also weigh them. So we can make some of the lines thicker than others to indicate that there is a stronger relationship between these 2 pair of nodes and a weaker relationship between these 2 pair of nodes. And this is like I said, it's a weighted network. And sometimes, sometimes you may also be interested in directed networks. So this might be, say, a dating network. So this may be a high school girl and a high school boy, and they date a lot, but they also date somebody else. And of course, dating is not directional. If 2 persons dated each other, then that you can just draw a link between them. There's no sense of some kind of directionality between the relationship. But in other cases, let's say a gene expression network, then there is a sense of directionality. You can put arrows into the network, and the network will indicate some kind of causal relationship. Let's say, this is gene A, this is gene B, and if you draw an arrow from gene A to gene B, that means that gene A actually promotes the expression of gene B. Okay? So this is a directed network, and well, we study all kinds of networks, and of course there are more exotic variants of networks like hypergraphs that I won't talk really much about for this particular talk. Now, when network scientists study a network, what do they study? Well, first they study the structure of the network. So they would ask questions like, what are the properties associated with the nodes? Like, for example, the degree. The degree of a node would be how many links are actually incident on the node. For example, this particular node, you can count 1, 2, 3, 4, 5. So it has degree 5. And then another node here would have degree 2. So in a complex network, unlike a regular lattice, the degree can vary from node to node. And the other thing that we might be interested in would be clustering. That means that if I look at this particular node here, it has a large number of neighbors. So 1, 2, 3, 4, 5, and 6. And then you can start asking, how many of those neighbors are also neighbors of each other? So that the kind of property is called clustering. So how easy it is to find a tight cluster of nodes. And then the other nodal property would be something called assortativity. Or in the social science, it is called homophily. That means, how likely it is for a node to be connected to a node that is like itself. So if you only have undirected, unweighted networks, then the kind of quality that you can use to judge whether 2 nodes are similar to each other would be just what their degree is. So this node here has degree 6, and is connected to this node here, which has degree 5. So the homophily is quite high around here, but then you have to average over the network. Now, the other kind of properties that you can measure that has to do with the structure of the complex network would be associated with paths through the network. First of all, you can measure the diameter of the network. That means what is the largest number of hops you need to that you can actually do on this network. So because some of the nodes are close, to each other, and then some of the nodes are further apart. Like from here to here, we need to hop 1, 2, 3, 4, 5, 6 hops, and there might be a shorter distance. Then that would be the distance that I will use to characterize the diameter of a network. And of course, I can also measure the average path length. And another concept that network scientists like to measure when they study the structure of a complex network is something called betweenness. That is, if I am sitting here and there are many paths that passes through me to go to another node, and the more such paths that passes through me, then I have a higher betweenness. So I am important. So if you remove me from the network, then the paths all fall apart. It's no longer possible to connect to each other. For example, there was the volcanic eruption in Iceland. It disrupted the European airline network, and turns out that people from Africa cannot travel to Asia anymore. They don't want to travel to Europe. They want to travel to Asia, but they cannot because the hubs are in Europe. Okay, there are no other hubs that will connect them once the European hubs goes down. So these betweenness is another important structural information that you want to get from the study of complex networks. Now, besides structure, which is static, we also want to see what happens if we put some kind of dynamics on the network. So one of them would be also motifs, but I won't talk about that. So let's say we introduce a epidemic kind of dynamics on this complex network. Let's say at time t equals 0, let's make this node here infected. And let's say the infection is a very highly viral disease, and it will infect anybody that is that is next to the infected node. So at time step 1, these nodes will become infected. But let's say that this super virus is also very short-lived. It produces a very short infectious period. The next time step, this fellow recovers, but then all the other nodes that were connected to the first generation of infected nodes got infected. And then you can go on, and then go on further. So eventually, after 5 time steps, only one node is still infectious. The rest have recovered and cannot be infected again. Okay, so that's SIR dynamics. That's dynamics on top of the network. But we can also talk about dynamics of the network. So this is the initial network, and we can do things to the network itself. We can, for example, we can add new links. So here I've shown in red the 2 new links being added. I can also add new nodes. So here I've shown 2 new nodes being added, one with 1 new link form, and the other one being connected to the overall network by 2 new links. Okay, so keep in mind these things here because they are important to the story that I'm trying to tell. Okay, so now let me fast forward a little bit. Obviously, there are lots of topics and questions that you can ask about complex networks, but the one I feel is interesting or important to the problem of information processing has to do with modular networks, or more recently, people have studied network of networks. They are slightly different. So this is a modular network. You can see that the different modules in this network is colored differently. So the red nodes are more closely connected to each other. The green nodes are more closely connected to each other, and then the different modules are only weakly connected between each other. Okay, this is a network of networks, and the distinction between modular network and network of networks would be that in this modular network, all the links are the same type. That means, if this is a dating network, then these are 4 different high schools. Once in a while, you date a girl from a different high school, but that's okay. But most of the time, you date people from your own high school. Whereas a network of networks, you should imagine the internet. So that's the network between computers. And then on top of that, the power grid. So that's a different network. But they're interconnected to each other. If the power grid goes down, of course, the internet goes down. If the internet goes down, sometimes the power grid also goes down. It depends on the kind of interdependencies they have. So that's in a network of networks, you can allow different types of connections between nodes. Okay, and if I don't know that there exist modules, I can discover them using many community detection methods that have since been developed. So it's a straightforward problem right now to detect the communities. Now, what happens when you put dynamics on top of modular networks? Okay, so this is what will happen if you have just a random network. So if you take a bunch of nodes and you connect them randomly, and then you put the SIR model on top of it, you get an infection curve that looks somewhat like this. A typical kind of infection curve that you see in, let's say, the flu pandemic, the flu epidemic, and maybe more recently, the Zika infection. Okay, but once you go to a modular network, then you find things like this, little spikes. So what is happening here is that the red module first got infected, and because the connection between the red and the green modules are weak, the green module don't get infected until sometime later. And then, of course, once one green node gets infected, the rest of the green nodes get infected very quickly, and then you wait for a while before the blue nodes get infected. So modular network progresses through this kind of cascade dynamics. If you put any kind of dynamics on top of it, it can be synchronization, can be SIR, can be various kinds of models, dynamical models you can put on it. You will see generically this kind of feature. And so far, I've not talked about anything that is speculative. These are all very well known. So cascade dynamics in modular networks have been discovered since the middle of the previous decade. And then for network of networks, they found the same thing effectively, starting from 2010, 2011, and then wrapped up more recently, 2016, just last year. So we see effectively the same kind of dynamics. Okay, so that's where the more concrete results end, and where I start speculating. So you see one star already. So I will start talking about how modular networks, the kind of dynamics that you see on modular networks is like information processing. So this is the same modular network again. I've shown the infection curves for, let's say this is a random network, and these are the cascades across the modular network. So if the red module get infected first, this is it. Okay. Then, of course, because the green module is connected to the red module, the green module get infected. And then after that, the blue module get infected. And this cascade sequence, I would like to say and claim that it's actually information processing cycle. Okay, I have a PhD student who is working on this, but he has not yet generated enough results that I can show. So that's why this is remains speculative. But otherwise, I think if I say this out loud, people would not feel that it is too much of a stretch. Okay. And dynamics, the information processing dynamics that is implemented in this way is robust because you don't have to rely on a single node. The whole modules will participate. Well, not all of it, but significant fraction of the module can participate. It is sensitive because it's amplified within a module. It is selective in the sense that if I change the input slightly in the red module, I can switch the pathway. I don't have to go through the green to blue pathway. I can go to the yellow and blue pathway. So there are this kind of selectivity that I can exercise if I do information processing this way. And I speculate that it is very similar to information processing that actually goes on in the human brain and other kinds of brains. Okay? And now that's the first speculation that I'm going to make. The second one has to do with the evolution of modularity. So we see a lot of modular networks in the world. They are usually associated with complex systems, but why are they modular? Is there any particular advantage of them being modular? Well, and if we see things from the perspective of information processing, okay, then we should contrast it against something that looks like this. This is a random network. It is nearly complete. In the sense, a complete network is one where all the nodes are connected to each other. And for a network like this, you will see this kind of infection curve. So just one broad peak, nothing much. Whatever you feed into this system, will just give you this. So it cannot discriminate between inputs. So all inputs give roughly the same output. Okay. Now, what if I now progressively thin out the network? What if I remove some links to produce a semi-modular network that looks like this? Now what happens is that because if the infection starts somewhere and it is relatively isolated, and you will start by producing a first infection peak, and then eventually, of course, the other parts of the network gets infected as well, and then you will go on to produce the second peak. And the reason why we have two peaks is because now we have actually separated timescales. So we have timescales inside a module and timescales between modules. But of course, if we just do something like this, then the peaks are not resolved. So you can say that this is like a very primitive information processing, but it's not good enough to, maybe for an ancient animal looking at a leopard and a zebra, it will run away from both, when in real life it only needs to run away from one. Okay? So eventually, if we thin out enough, we get to this kind of modular structure. We would have very well-defined cascade structure, resolved peaks, and then we can start to really talk about information processing. So the modularity, so I believe modularity emerges as a result of selective information processing, and we are in the process of testing this in a model, of course. After we test it in the model, of course, there is someone in NTU who can grow neurons on Petri dishes. We would like him to actually test it on the Petri dish to see whether it will work. And then after that, maybe we will ask to see whether we can do it on the real brain. But that will be many, many years from now. Okay? So now, to the highly speculative part of the talk, how would these things become different? If the networks themselves are not classical but quantum. Okay, so the same modular network again, the same kind of cascade. These are the classical cascade dynamics. Well, at the very least, if quantum mechanics don't play an important role, then at the very least, we expect the same cascade dynamics to play out on a quantum network. But of course, quantum mechanics is inherently rather different from classical networks. So we expect first, there is this path here, and there's this path. Classically, you take only one path, because once they interfere with each other classically, you may get nothing here. Or you just get enhanced here, so that the results are not very discriminating. But when you have quantum mechanics, then you allow for the interference between paths. And of course, we know in dirty metals, this kind of interference between paths produces weak localization. So we don't know whether something like this weak localization will also happen on quantum complex networks. That would be very interesting to see. And then of course yeah. Yes.
What do you mean by quantum network?
That means the nodes themselves are quantum degrees of freedom.
What if not a channel like quantum, like the edge of not?
The edge, of course, should be a quantum channel as well. So everything should be quantum. Yeah. Because if you have a quantum node but just classical connections, maybe I think you only get the classical results. Yeah. But I can't be sure. I'm just speculating.
I'm just thinking about this like a quantum random walk.
There is something about detection of, I don't remember exactly the details, but detection with quantum walk.
Community detection, right? There was one.
Yeah. Yes. So that's for community detection. So but that's to detect on a that's for community detection on a classical. Okay. So yeah. In the sense that the network is classical and it is also static. So there's no dynamics. The dynamics you impose for the purpose of discovering the communities. Yeah. And of course, after you detected the communities, you can start doing imposing more interesting dynamics on top of it. And of course, if once we go to quantum, then the order of excitation may matter. Obviously, and the reason for that is because in neurons, once a bunch of neurons fire, they cannot fire immediately after. They have to actually take time to recharge before they fire again. So if we want something similar in quantum networks, then we may have to consider different kinds of excitations. So whether we want to impose bosonic, fermionic, or anionic excitations on these nodes themselves. And of course, the links, you can design different kinds of quantum links between the nodes. And of course, in a classical network like this is a cycle, so it's a bubble. And in the classical network, the bubbles don't really do anything. They just allow you two paths to select. But in a quantum network, some of these once you have a bubble, you may have virtual processes that are not observed unless you design measurements to observe them, and they may actually produce other measurable outcomes if you do. Okay. Now, then this is the harder part. So I speculate further on how it is possible to allow quantum complex networks to evolve the network itself. So if you start from something like this and you want to go to something like this, how can we do that? Because here I've kept the number of nodes the same, but the links have changed. The number of links have changed. So it's like, I have a circuitry, a quantum circuitry, and then I just cut one of the links. Of course, the experimentalists will kill me if I do something like that. But theoretically, we want to have some kind of formalism for which we can add links and add nodes. So I think the way to do that would be to actually abandon working with Hilbert spaces, but to work with Fock spaces. So this is a many-particle representation where we can go from just one node, two nodes, and one link to any number of nodes and any number of links. And I'm sure by working in such space like this, we would have a lot of interesting results that are very different. So questions like, whether quantum networks are more modular than their classical counterpart, we can ask questions like this. I don't know the answer.
So
yeah.
This is a very speculative question on a speculative topic.
Yes.
Then would you end up in a situation where you might have a superposition of a link and not a link, or a superposition of weak link and strong
Yes,
link?
yes. Yeah. Yeah.
That'd be very weird.
Yes. And I've not seen anyone done something like this. For particle physics, people have to work with Fock spaces for a while, but for networks, I think nobody has done anything that resembles this remotely. So I wouldn't say that I have a conclusion, but I point out a possible roadmap. And these are, the information processing that I talk about now here, they are interaction mediated. So you don't have externally imposed logic gates, like the kind of I don't remember the Hadamard gates and control NOT gates that you guys are much more familiar with. And of course, in the brain itself, there are no logic gates. There's nothing that looks like a NOT or XOR, but they are just neurons connected to each other. Classically, we are okay working with that, but quantum mechanically, I'm not sure how we would describe that. Importantly, we must be able to come up with a quantum description of the cascade. And the cascade plus the quantum effects may lead to weak localization. And of course, one phenomenon that is possible in quantum mechanics that is not possible classically would be tunneling. So you may have a information cascade that goes on one path and then tunnels over to the other branch. That is definitely not possible in classically, but who knows whether it happens in a quantum network. And obviously, in order to go on to attack the second speculation, the most speculative one, we would need to have some kind of a quantum description of network evolution, which I believe doesn't exist right now. So, and how quantum mechanics may select for modularity, I think I have a good feeling for how classical networks select for modularity. It's a question of it's simply a question of two opposing forces. One, to be able to represent as many different inputs as possible, and the other one is to be able to reproduce them correctly. Because if you try to reproduce too many, then the same input may be overrepresented, or you may have two inputs giving you the exact same output. So those are the things that you don't want, and I think that's the kind of forces the complex networks, classical complex networks, to evolve into modular ones. But we don't know whether there are equivalent selection forces that's at play when you now make it quantum mechanical. Okay, and I think that's the end of my talk.